And welcome back to another video tutorial for statistics. Now, today we are going to talk about non-parametric analysis. If you remember, a parameter is a statistic that describes a population, like mu and sigma, or the mean and the standard deviation of the population. In order to calculate parameters, we need to use interval or ratio scale data. That way we can calculate an average number of words recalled or an average score on a test, so on and so forth. However, there are other types of scales that don't have numbers associated with them. Do you remember what they are? Well, hopefully you said nominal data, and even ordinal data to some extent. But nominal data, if you recall, are data that don't have any numerical properties. They are more about categories. For example, gender is a nominal variable, with male and female being the two subcategories, or hair color with blonde, brunette, red, black, and so on. Diagnostic label like depression, PTSD, schizophrenia, so on and so forth. Well, we still do research with nominal data, but we can't calculate means and standard deviations, so we can't analyze the variance or compare the means like with t-tests and ANOVAs. Enter non-parametric tests. Non-parameter tests, non-parametric tests. The key point to remember here, well, there are several key points, but we want to remember that the non-parametric tests, specifically the chi-square goodness of fit test, that's the test that we are going to be describing today, is not used to identify the cause and effect of variables, one variable on another, but rather to look for patterns, deviations from what we would expect from chance. And there are two types of chi-square analyses. There is a one variable chi-square test, which is used to just see if the frequencies that you observe in a given nominal variable differ from what we expect by chance. And in the next video, I'll be describing a two-variable chi-square test of independence, which is used to see if two variables are related in some way, or if there is an association between those two variables. Okay? But for this variable, we're going to focus on, or this video, we're going to focus on the one variable test. Okay, what I've put up here now is the actual formula for the chi-square test. And it's the same whether it's a one variable or two variable test. First off, I want to say that the actual symbol for chi, the Greek letter chi, is a real fancy curly X, the little squared symbol there. I didn't take the time to find that particular symbol when I typed it out, so I just used an italicized X. But anyway, chi, and that's how it's pronounced, chi, C-H-I, is simply the sum of the observed frequencies minus the expected frequencies squared divided by the expected frequencies. So O equals observed frequency and E equals expected frequencies. There we go. Observed and expected. Now you might be saying to yourself, what do you mean by observed and expected? Well, by expected, we really mean what would happen by chance alone, just randomness in the world without any pattern. So let's clean up some of this stuff and give an example, and all of this will start to make more sense. Okay, what I put up here now are some hypothetical data for a marketing research project. Specifically, I want to see if sex in advertising has an effect on product sales. So I get a group of people together, and if we add this up, we see 8 plus 12 plus 40. We have a total N of 60 individuals. Okay, actually, let me put that up here. We'll erase this. And we have an N of 60. Now, I show them 3 commercials. One commercial is just bland facts about the product. Another one maybe has some kind of storyline or is a little more interesting, but we'd say it's ho-hum, definitely not sexual. And then there's the hot and steamy commercial. So we show them these 3 commercials and we ask them to indicate their likelihood of buying the product. And you see from the data that 8 people said that they were interested in the product when they saw the bland commercial. 12 people said that they were interested in the product with the ho-hum, and a whopping 40 people when it was hot and steamy. These numbers are the observed frequencies, okay? Observed frequencies, because it's the actual numbers that we saw in our research project. Now, we have to calculate, we have observed, now we have to calculate the expected frequencies. So to do that, I'm just going to put some cells down here. Okay, if we have an N of 60, and there really is no effect whatsoever of commercial type on purchasing decisions, then how many people would we expect to fall into the 3 categories here with no effect of all of the category? Well, it's simply 60 divided by the number of cells, in which case there is 1, 2, and 3 cells. We would distribute those 60 people evenly. So we would have 20 people in the bland category. We would expect another 20 in the ho-hum and 20 in the hot and steamy. This is the expected frequency. All right, all I did was I take N and divide by the number of cells in the study. Okay, we just distribute those 60 people evenly across the 3 groups. So we now have our observed and our expected, and we can plug them into the formula. A couple of quick points that are very important that you really need to commit to memory. The first is that in chi-square analysis, to be valid, none of the expected cells can have 0 for an expected frequency. And we've got 20, 20, and 20, so clearly none of these are 0, and that's not a problem. But also, no more than 20% of the cells can have an expected frequency of less than 5 observations. And once again, we have 20 in all of these, so we're not even near being less than 5. But if we had any cell with 0, or more than 20% with less than 5, like a 4 or a 3 or a 2 or a 1, then we would not be able to do a chi-square test because it would be too invalid, too unstable, if you will. Okay, so remember those 2 rules. They're very important, and they can definitely come up on homework or an exam. So back to the problem. We have to sum up observed minus expected squared divided by expected. So what we do is for each cell, we take observed, which was 8, minus expected, which was 20. We square that difference, and we divide by the expected value for that cell, which was 20. Now we have to do that for all 3, and because there is a sum symbol in the formula, we just add them together. So we go to the ho-hum cell, and we have a 12 minus 20, observed minus expected, squared, divided by expected. And we do the same thing for the hot and steamy commercial group, which was 40 minus 20, observed minus expected, squared, divided by 20. And then we just do all of the math. We solve each of those little ratios and add them together, and we end up with, we end up with a chi-square equal to 30.4. That is the statistic, just like F or T. It's that simple. Incidentally, we are testing the null hypothesis that there is no effect of commercial type on product purchasing decisions, and we're comparing that to the research hypothesis that there is an effect of commercial type on purchasing decisions. Okay, I want to make that clear. We're always testing these null versus research hypotheses. Well, we now have a chi-square value, a calculated chi-square, and just like with z-tests and t-tests and f-tests, we now need to compare that to some critical value. That is the value that would happen just by chance alone, just by the sample that we happen to get 5% of the time. And to do that, we turn to the chi-square distribution table. It's in the back of your textbook, table X. Excuse me. And I'm going to open up a new window here. All right, clean things up once again. We have a chi-square of 30.4. We have an n of 60. And the other thing that we need is degrees of freedom. And the degrees of freedom is easily calculated. It is the number of cells minus 1. Cells minus 1. In this case, that is 3 minus 1, or 2. We have 2 degrees of freedom in this particular experiment because we have 1 cell, 2 cell, 3 cells. Now we can look up our critical value. In the table in your textbook, you'll see a column labeled degrees of freedom, and it will start at 1 and 2 and 3 and 4 and dot, dot, dot. And a little further over, we're going to go to an alpha of 0.05. So we look where 2 degrees of freedom would occur 5% of the time. And if you do that, the critical value comes out to be 5.991. So we now have our critical value of 5.991 that we compare to our calculated chi-square value of 30.4. And just like T and F and Z and all of the other things that we've done so far, anytime our calculated value is larger than our critical value, that means we're in a range that would occur more than 5%, less than 5% of the time. And so, is this significant? Well, clearly 30.4 is greater than 5.991, so yes, it is significant. And if we were to write that out, let's see if I can give myself some space here. We would simply write out that we did a chi-square test with n of 60 and 2 degrees of freedom equals 30, sorry, this is not writing very good, 0.4. And our p is less than 0.05. Hopefully that made it into the video. That is the way you write up the results of a chi-square analysis in APA format. We did a chi-square, we tell the reader what our n was, we tell them how many degrees of freedom we have, what the value of chi-square was, and then lastly, the probability of getting that by chance. If this was not significant, the only difference that would occur is we would have put the greater than symbol there. The p is greater than 0.05. But because ours was significant, we simply say that it was less than 0.05. The probability of getting our chi-square value just by chance alone is less than 5%. And that, ladies and gentlemen, is all there is to it to calculating a chi-square analysis with one variable. So then we just have to interpret the results. And to do that, we simply look back at the data and we sort of describe what the pattern is. We know it's a real pattern. It's not just by chance alone. So looking at the numbers, what would you say? Does sex have an effect on sales? And in this instance, if it does, since we concluded that it was significant, we're going to say that it does. What effect is it? Well, here the effect is that the more interest or sexually engaging a TV commercial is, the greater the sales. Because we had 40 people interested in the product under that hot and steamy condition compared to 12 or even 8. And that's really all there is to it with the one variable chi-square test. Now, the next video is going to describe what we do when we're comparing two variables. We want to see if two nominal variables are related in some way. Once again, it's the same chi-square test with the same formula of observed minus expected divided by, or squared divided by expected. The only slightly more complicated part is how we calculate those expected frequencies. So when you're ready, fire up that next video and you'll see that it's also not that much more difficult to do a chi-square with two variables. Okay, thanks for watching.